All right, we're about to have a big breakthrough. The area under the velocity curve gives distance traveled. But remember, we already know that velocity and distance traveled are related. Velocity is the derivative of distance. So it turns out you can find the area under any derivative curve to find out how much the original function has changed over an interval. So we have to understand what we mean by original function. So if position's derivative is velocity, then I can find the area under the velocity curve to find the change in position. So another way to think derivative is rate of change. So here's an example. This example would never cut it in a free response section, because here we're going to have to use rectangles. We have to use something to approximate area under a curve, and we haven't been told what kind of approximation to give. But it's a multiple choice question, so that's why they can be not specific. Here, the production rate of cola in thousands of gallons per hour. Notice this word per. It's our hint that we're talking about a rate of change, gallons per hour, at some production plant on some day is shown in the graph. To the nearest round number, how many thousands of gallons of cola were produced that day? Well, to find the change in the number of gallons of cola, you find the area under the rate of change in the amount of cola curve. So production rate is the derivative. And that's what's in the graph. We're going to find the area under that curve to give the total amount of cola produced over that time period. This is hours measured from 0 to 24. We've been told that the output axis is marked in thousands of gallons per hour. So here that's 100,000 gallons per hour. So here we're just going to try to approximate the area under the curve. We're looking for a round number. If I was going to count rectangles, I see 1, 2, 3, 4 whole rectangles, 5, 6 whole rectangles. Maybe I decide that this and this together add up to a 7th rectangle, and this add up to an 8th rectangle. So that tells me that I have 8 rectangles. Every rectangle is 6 hours wide. And how tall is it? 100 thousands of gallons. So I'm going to use the number part here and then thousands of gallons as a unit. So that's 8 times 6 is 48 with 2 zeros, so 4800. That's thousands of gallons per hour times hours. So that's 4800,000 gallons. All right, here's one that's similar. Hope you recognize this setup from your test. The volume of hot air in a balloon increases as the air inside is heated. And the radius of the balloon, therefore you can assume, since the volume is increasing, the radius must also be increasing. Is measured in feet, and it is given by a function r. We've been told r is twice differentiable. All that means is we promise that r double prime exists. It implies that r is continuous and smooth. T is measured in minutes. We've been told that r is concave down for 0 to 12, and that's the whole interval of this problem. And we have selected values of r prime. That's the rate of change of r. That's the same as saying dr dt. We've been asked to use an r-ram approximation to find out how much the radius of the balloon changes over the interval 0 to 12. Indicate units with our answer. So, see the part where I said I modified this? Clearly, when I modified this, I didn't remember to include how many rectangles you should use. So let's assume that this said use an r-ram approximation with 1, 2, 3, 4, 5 intervals. Usually the wording on the test is they'll say, use the 5 intervals suggested by the table to give an RRAM approximation. So we can see that the 1, 2, 3, 4, 5, 6 input values in the table give us 5, 3, 4, 5 intervals to check over. 5 intervals to use as the widths of our rectangles. It's going to be our job to figure out the height of each rectangle and add up all those areas to give an approximation. So I'm going to leave the units off and put them in at the end, just because I think I'm going to have trouble fitting this whole Riemann sum across here. So I'm going to use the areas of 5 rectangles to figure out how much the radius of the balloon increases over the time 0 to 12. Notice what's going on here. I have 5 rectangles. They do not all have the same width. That's pretty common on the AP test because there's some fun advanced tools you can get for your calculator that will compute RRAM and LRAM and MRAM when you do have the same intervals, and they don't want any student who can get the fancy software to have an advantage. So they specifically write these problems so that everybody has equal footing. It's just our job to notice now. I'm going to have to pay attention when I write down the width of my rectangle. So the first rectangle covers a distance 0 to 2. That's a width of 2. RRAM says use the rightmost endpoint of the interval, in this case 2, to figure out the height. That tells me the height is going to be 4. That's the area of my first rectangle. My second rectangle covers the distance from 2 to 5. That's a distance of 3. And what height am I going to use? I'm going to use 2.0. That's the height from the right end of the endpoint of the right endpoint of the interval 2 to 5. My third rectangle covers from 5 to 7. That's a width of 2. The height 1.2. My third rectangle covers the distance, a long distance, from 7 to 11. That's a distance of 4. So a width of 4 for that rectangle, a height of 0.6, plus one more little rectangle at the end. It covers from 11 to 12. That's how I know the width is 1, and the height is 0.5. So I took a little break there to do all my adding. So again, this is areas of 5 rectangles, so I'm going to do all these multiplications and add the areas of the 5 rectangles. I get 19.3. Notice I've been asked to include units with my answer. So just go back and look at each of these little multiplications I did. 2 times 4. 2 was a distance across the time interval, which was measured in minutes. And the 4 was a height, so like an output value of this function. What function? R prime. And R prime of t, we've been told, is measured in feet per minute. Now notice I only considered the units on that first rectangle, but I'm not going to be able to add up 5 rectangles areas if those areas don't have the same units. So that's the whole idea. You want to check for this parallel structure. If you don't have 5 little expressions that mean multiply a time value by a feet per minute value, like a minutes value times a feet per minutes value, then you don't have expressions that you can add together. You can't add things together unless they're like terms. Like terms means they have the same units. So here, 19.3 minutes times feet per minute, that makes 19.3 feet. And notice that matches. We were approximating a change in the length of the radius. And we've been told that the radius, where is it, is measured in feet. Notice I didn't ask, but I see now I should have asked. 19.3 feet. Is that an overestimate or an underestimate of the actual change in the radius between time 0 and time 12? I'm going to write that answer. It was 19.3. So what is it that I have to consider to decide if 19.3 is an overestimate or an underestimate? Well, I was finding area under the R prime curve. And we said, and I was using RRAM. We said RRAM is going to overestimate for increasing when you try to find the area under an increasing function. That's increasing to me. Is that increasing to you? Yeah. And then RRAM is going to be an underestimate if you have a function that goes downhill. If you have a decreasing function, then your RRAM is going to be an underestimate. Yes. So I'm going to have to make a decision. R prime, because that's the curve that I was finding the area under. Is there a way I can find out if it was increasing or decreasing? So here's the hint. R is concave down, which means that R double prime must be negative. If R double prime is negative, that tells me that R prime must be decreasing. Right? Because R prime prime, if R prime is decreasing, then R prime prime must be negative. And I know R prime prime, R double prime, is negative. So I'm going to write up my answer. So their answer I've written up, 19.3 feet is an underestimate of the true value of the radius because R prime is decreasing.